No falls, but it is made of metal. Far beyond our solar system, a planet endures a storm of scorching sand and molten glass. This is the incredible exoplanet VHS 1256b, a super Jupiter where the weather defies every rule we know. By the end of this journey, you will understand the physics of a world where the sky rains rock. How can a cloud be made of mineral vapor? And what does a blizzard of liquid iron even look like? What is the strangest weather you can possibly imagine existing on another world? This bizarre world was first spotted in 2015, not by a space telescope, but by a powerful eye on the ground in Chile. The Vista Survey telescope, scanning the southern skies for infrared light, picked up a faint, warm glow from a seemingly empty patch of space within the constellation Corvus. The source was about 40 light-years away, a distance so vast it takes light itself 4 decades to make the journey. Astronomers quickly realized this was no ordinary planet. The object, named VHS 1256b, was an enormous ball of gas many times more massive than Jupiter. It sits in a strange category between a planet and a star, often called a super Jupiter or even a brown dwarf, which is essentially a failed star. It never gathered enough mass to ignite the nuclear fusion that powers a sun, so it simply smolders with the leftover heat from its violent birth, and its orbit is almost incomprehensibly wide. It circles not one, but 2 central stars, and it is so far out from them that a single orbit takes more than 10,000 years. For context, all of recorded human history would fit inside just a fraction of one of its long, slow years. This immense distance and its relative youth, estimated at only about 150 million years old, made it a perfect target. Isolated from the blinding glare of its parent stars and still glowing fiercely with its own internal heat, VHS 1256b presented a pristine, uncluttered laboratory in the sky. It was an open book waiting for an instrument powerful enough to read its pages. That instrument would soon arrive, and it would rewrite everything we thought we knew about alien weather. This immense distance and searing internal heat forge a world of almost unimaginable extremes. VHS 1256b is a monster of a planet, a super Jupiter with over 12 times the mass of our own solar system's king. If you could stand on a platform near its cloud tops, you would be crushed by gravity more than 20 times stronger than Earth's. The temperature there is a blistering 800 degrees Fahrenheit, hot enough to melt lead and zinc with ease. But the true chaos comes from its spin. This giant completes a full rotation in just about 1.4 Earth hours. A day there is a frantic blur. That dizzying speed whips its atmosphere into a frenzy, generating winds that scream across the planet at thousands of miles per hour. These are not breezes, they are planet-engulfing rivers of superheated gas. And below those churning clouds, there is no solid ground to crash upon, no continental shelf or mountain range. The atmosphere simply grows denser and hotter as you descend, eventually turning into a strange, metallic fluid under unimaginable pressure. This is a world defined entirely by its sky, a cauldron of perpetual storm where the very idea of weather is rewritten into something terrifying and magnificent. Into this swirling chaos finally came a tool with the vision to see it clearly. The James Webb Space Telescope turned its golden eye toward VHS 1256b in 2022, and what it saw was not just a blurry dot of light, but a detailed chemical portrait. The telescope used 2 of its most powerful instruments to dissect the planet's faint glow. The mid-infrared instrument, or MIRI, and the near-infrared spectrograph, NIR-SPEC, worked like the most advanced prisms in history. They performed a technique called spectroscopy, which is the true magic behind understanding distant worlds. Here is how it works. When light from the planet, which is really just a mix of its own internal heat and the reflected light from its stars, passes through its own atmosphere, the gases and particles there leave unique marks. Specific molecules absorb very specific colors or wavelengths of that light. The telescope captures this altered light, and then scientists spread it out into a full spectrum, a rainbow of infrared colors. Across that rainbow are dark lines and bright bands, a barcode of chemistry. Each dip and peak is a fingerprint, revealing the identity of the substances floating in that alien sky. The astronomers were looking for these fingerprints, and what they found was astonishing. There, in the data, were the unmistakable signatures of silicate grains, tiny particles of sand and rock, but floating high up in the atmosphere. Alongside them was the clear signal of water vapor. This was the eureka moment. It was not just a detection, it was a snapshot of the weather in action. They were seeing the actual ingredients of the clouds, caught in the act of existing in a place where no one thought clouds like this could form. The telescope had not just observed a planet, it had tasted its stormy skies. The data from Webb painted a picture of a sky in violent, layered motion. To understand the metal snow, we need to descend through the atmosphere of VHS 1256b, layer by treacherous layer. At the very top, where the telescope can peer most clearly, lies the visible cloud deck. This is not a blanket of soft white vapor, but a churning, tempestuous haze of tiny silicate particles. Think of it as a global sandstorm, but the grains are not blown from a desert below, they are born in the sky itself. The composition is eerily familiar, the same minerals that make up sand and glass on Earth, quartz and enstatite, but here they exist as a fine, scorching mist suspended in an alien air. This is the layer we see, the planet's stormy face. Beneath this visible deck, the atmosphere plunges into deepening chaos, governed by a simple, brutal rule. The deeper you go, the hotter and more crushing the pressure becomes. It is a vertical furnace. Down in the lower atmosphere, temperatures soar to over 1,500 degrees Fahrenheit, a heat so intense it vaporizes rock. At those depths, silicates exist not as grains, but as a vapor, a mineral gas mingling with other exotic compounds. This is the source material for the entire weather cycle. Now follow that hot, mineral-rich gas as it rises. Powerful convection currents, fueled by the planet's internal fire and its furious spin, carry this vapor upward. As it rises, the pressure drops and the air expands and cools. It is the same basic physics as a steam cloud cooling and forming water droplets, but with a radically different ingredient. Somewhere in the mid-atmosphere, a critical threshold is crossed. The temperature in this rising column of vapor drops just enough, perhaps to around 900 degrees, for the magic, or rather the physics, to happen. This is the condensation zone. In this narrow band of the sky, the silicate vapor can no longer remain a gas. It begins to condense, first forming tiny droplets of liquid rock, molten glass, and then, as it cools further, solidifying into microscopic grains of sand. These newly formed particles are what we detect as the upper cloud deck. But the story does not end with clouds. What happens when these tiny, solid grains grow heavier, when they can no longer be held aloft by the furious winds? They begin to fall. This is the precipitation of VHS 1256b, a downward blizzard of mineral snow. Yet this snow does not reach a solid surface. As the grains descend back into the deeper, hotter layers, they are reheated, sublimating back into a vapor, ready to be lifted once more to begin the cycle again. The planet is caught in an endless, scorching rain dance where the sky both creates and destroys its own storms. This endless cycle hinges on a chemical recipe written in extreme heat and pressure. To create a blizzard of sand, you first need to turn solid rock into a gas. Deep within the lower atmosphere of VHS 1256b, where pressures are thousands of times greater than Earth's surface and temperatures exceed 1,500 degrees, common planetary building blocks undergo a radical transformation. Silicate minerals like enstatite and forsterite, which form much of the rocky mantle deep inside our own world, cannot remain solid here. They are literally cooked out of their rocky state. The immense thermal energy overcomes the forces holding their molecular structure together, forcing them to sublimate, turning directly from a solid into a vapor. This creates a layer of mineral fog, a dense, hot mist of silicon and oxygen compounds mingling with other exotic gases. It is a cavern of vaporized stone. From this deep reservoir, the planet's furious dynamics take over. Powerful convection currents, like the updrafts in a thunderstorm but on a planetary scale, act as an elevator. These rising columns of superheated gas grab hold of the silicate vapor and carry it upward, away from the crushing depths. As this parcel of air rises, it enters a realm of decreasing pressure. The gas expands, and in doing so, it cools. This is a fundamental rule of physics, the same reason the air gets colder as you climb a mountain. The journey upward might span hundreds of miles, and the temperature plummets by hundreds of degrees. Then, at a specific altitude in the mid-atmosphere, the environment crosses a critical threshold. The temperature drops to a point, perhaps around 900 degrees Fahrenheit, where the silicate vapor can no longer remain a gas. It reaches its condensation point. Think of a cloud forming in Earth's sky, where water vapor cools and condenses into liquid droplets. Here, the vapor is not water but mineral. The silicon and oxygen compounds begin to cling together, nucleating around microscopic seeds of dust or salt. They form not soft water droplets, but tiny, incandescent beads of molten rock. This is the moment of creation for the clouds we see. These droplets, a rain of liquid glass, continue to cool as they are buffeted by the winds. Many will solidify further into fine, crystalline grains, a glittering sand suspended in the sky. This is the metallic snow in its nascent form, a storm born from vaporized mantle and sculpted by the vertical furnace of an alien world. These newly formed grains of sand and droplets of molten glass cannot float forever. Gravity is a patient and relentless force, even on a world of chaos. Once a silicate particle grows heavy enough, or once the turbulent updrafts that birthed it weaken, it begins its long, final descent. This is the moment the cloud becomes rain, or rather, a downward blizzard of scorching mineral. Picture a single microscopic grain of enstatite, a speck of sand forged in the sky. It starts to fall, plunging through the churning atmospheric layers. At first, the winds may still buffet it sideways in a 1,000-mile-per-hour horizontal rush, but the net direction is down into the deepening furnace. The journey is a one-way trip into increasing heat and pressure. As the particle sinks, the ambient temperature around it begins to climb again, from the 900 degrees where it formed back toward the infernal temperatures of the lower atmosphere. Long before it could ever reach any theoretical solid core, something extraordinary happens. The intense heat overwhelms the particle's structure once more. At a certain depth, the temperature crosses the threshold where silicate can remain solid. The grain does not melt into a droplet in the traditional sense. It undergoes a direct phase change. It sublimates. In an instant, the solid speck transforms back into a wisp of mineral vapor, disappearing into the hot, dense gas from which it came. This completes the cycle. That same vapor will eventually be caught by another rising convection current, lifted, cooled, and condensed once again into a new grain of sand in the high clouds. The entire atmosphere of VHS 1256b is engaged in a perpetual, violent recycling program. It is a global, scorching water cycle, but with liquid rock and metal sand instead of water. The sky is both the factory and the furnace, constantly creating and destroying its own storm. This means the planet likely has no calm surface, no moment of stillness, just an endless, searing precipitation that never truly lands, a sandblasting rainfall suspended forever in the sky. Yet the silicate snow is only one ingredient in this alien sky's volatile cocktail. The James Webb Space Telescope's spectroscopic analysis revealed a full menu of familiar molecules swirling in the chaos. Alongside the sand and rock vapor, astronomers detected the clear, sharp signature of water vapor. Finding water itself is not entirely unexpected on large gas giants, but its presence here, mingling with scorching mineral clouds, underscores the bizarre chemical laboratory at work. More surprising was the detection of methane, carbon monoxide, and carbon dioxide. On a planet this hot, conventional wisdom suggested methane should be thoroughly destroyed, ripped apart by the intense thermal energy. Its survival is a clue hinting at the atmosphere's furious churn. Powerful updrafts may be constantly dragging fresh methane from cooler, deeper layers up into the observable zone faster than the heat can break it down. Meanwhile, carbon monoxide and carbon dioxide tell a story of their own, markers of a carbon cycle playing out under extreme conditions. This mixture is profoundly significant. It means VHS1256b is not a monotonous world of uniform soup, but a dynamic chemical reactor. Different gases are mixing, reacting, and being transported in a giant, three-dimensional weather system. The atmosphere is a rich tapestry of elements where water, the building block of life as we know it, exists alongside the raw materials of rock and metal, all dancing in a heat-driven frenzy. Adding to this portrait of turmoil, the telescope data revealed another critical detail. The silicate clouds are not a smooth, uniform layer like a blanket of stratus cloud on Earth. Instead, the signatures indicate a patchy, broken deck with particles of varying sizes. Some areas likely have thicker, denser clouds of larger grains, while others are clearer with only a fine haze. This is the hallmark of a violently active weather system. It suggests towering convective storms where powerful updrafts create localized cloud banks and areas of subsidence where the sky is clear. The planet's face is not static. It is a roiling, storm-torn canvas where metallic blizzards rage in some regions while others offer a fleeting, hazy view into the deeper atmospheric layers below. This patchiness completes the picture of a world in constant, seething motion, a place where the weather is not just extreme but endlessly inventive. The sheer violence of this weather is not a permanent state for all worlds like this one. The raging storms of VHS1256b are a direct consequence of its cosmic infancy. This planet is astoundingly young, a mere 150 million years old. To put that in perspective, when dinosaurs still roamed Earth, this alien world had already been born, but it has existed for less than 4% of our own planet's long history. That youth is absolutely critical. A gas giant of this size forms from the gravitational collapse of a vast cloud of gas and dust. That process releases a phenomenal amount of energy, which becomes trapped as heat deep within the planet's interior. Because VHS1256b is so young, it has not had time to cool down. It is still glowing fiercely with the leftover fire of its own violent birth. This immense internal heat is the primary engine for its weather. It creates a tremendous temperature difference between the scorching deep layers and the slightly cooler upper atmosphere. Heat always moves from hot areas to cold ones, and on a planetary scale, that movement happens through convection. Think of a pot of water just beginning to boil. The water at the very bottom, closest to the flame, gets hottest first. That hot water expands, becomes less dense, and rises in great, bubbling plumes toward the surface. As it rises, it cools, then sinks back down along the edges to be reheated, creating a circular current. Now, imagine that pot is a planet tens of thousands of miles wide. The water is a mixture of hydrogen, helium, and vaporized rock, and the flame is the planet's own searing core. That is the convection driving VHS1256b. The internal heat creates these planet-wide updrafts and downdrafts, which are the vertical highways that carry silicate vapor up to condense and pull falling sand grains down to vaporize. Without this relentless internal furnace, the entire cycle would slowly grind to a halt. But heat alone does not create the frenzied chaos we see. This young planet also spins with dizzying speed, completing a full rotation in just about 1.4 Earth hours. A day there is a frantic blur. This rapid rotation acts like a giant spoon stirring the entire atmospheric pot. It takes those massive vertical convection currents and twists them, shearing them, and whipping them into a horizontal frenzy. This generates the supersonic winds that scream across the planet, creating a churning, turbulent maelstrom. The combination is what makes the weather so visible and so extreme. The youth provides the heat engine, and the fast spin provides the violent stirring. Together, they ensure the atmosphere is never still. Chemicals are constantly being mixed from deep layers to high clouds and back again, preventing any stagnant zones. This constant churn is why we can see methane surviving at the cloud tops, and why the silicate cloud deck is patchy and dynamic. It is a system in a state of furious, adolescent energy, a world where the weather is not just an event, but the very character of the planet itself, laid bare for us to see in all its scorching, stormy glory. All this talk of vaporized rock and metallic snow paints a picture in our minds, but what would it actually look like to stand in that sky? We have the chemical data, the temperature maps, the wind speed estimates, but a human eye will never see VHS 1256b directly. This is where science and art perform a vital collaboration. To translate the raw numbers into a visual scene we can comprehend, astronomers work closely with artists who specialize in space visualization. These are not flights of fancy, they are informed interpretations built layer by layer from the spectroscopic evidence. The starting point is the atmosphere's composition and temperature. A deep, hazy orange or red hue is almost certain, dominated by the scattering of light through a thick soup of silicate particles and other molecules, similar to how dust storms on Mars or pollution on Earth can redden a sunset. But this sky would not be a uniform blanket of color. The data shows patchy, varying cloud decks. This translates visually into a dynamic canvas streaked with darker and lighter bands. Imagine vast, swirling tempests of denser mineral clouds appearing as deep, rusty browns or charcoal streaks, while thinner hazes might allow a murky glow from the hotter layers below to shine through in brighter amber. The light source itself is a key part of the scene. The planet orbits two parent stars. From its distant vantage, they would appear not as blazing suns, but as intensely bright points of light in the sky, perhaps casting faint, double shadows through the thick haze. Now picture the precipitation. During a silicate downpour in a region of active convection, the falling grains and droplets would not be cold and white. They would be incandescent, tiny particles of molten glass and metal, heated from within by the planet's own thermal glow and illuminated from above by the twin stars, would streak through the atmosphere like a billion falling embers. It would be a blizzard of fire and glitter, a continuous, silent meteor shower contained within the sky. This breathtaking spectacle, however, stands in stark contrast to the source of our knowledge. The artist's vibrant impression is born from pages of graphs that look nothing like a world. The true portrait of VHS 1256b is a spectrum, a jagged line on a chart. Each dip and peak in that line corresponds to a specific molecule absorbing light. A small trough at one precise wavelength is the fingerprint of silicate grains. A cluster of tiny spikes elsewhere confirms water vapor. Another set of wiggles reveals methane. The artist's job is to take this barcode of chemistry and physics and render it into a scene that stirs our curiosity and makes the alien feel tangible. One is raw data, the other is human understanding, and together they allow us to visit a world we can never touch. Our own solar system offers a stormy giant for comparison, a world whose weather we once thought was the ultimate in fury. Jupiter, the king of our planetary neighborhood, is a titan of tempests. Its atmosphere is a churning tapestry of ammonia ice clouds, striped with belts and zones of screaming winds. The Great Red Spot, a hurricane larger than Earth that has raged for centuries, is a symbol of its enduring power. Deep within those colorful cloud decks, scientists believe colossal thunderstorms crackle with lightning 1,000 times more powerful than anything on our planet, driven by the condensation and freezing of water vapor far below. Jupiter is a masterpiece of violent meteorology, but its ingredients are strangely familiar. Ammonia, water ice, these are compounds we understand. Its storms, for all their scale, operate on principles we can recognize from our own world, just amplified to a staggering degree. This makes Jupiter a crucial reference point, a baseline for what a giant planet's weather can be. Then we look at VHS 1256b, and that baseline shatters. The differences are not just of scale, but of fundamental nature. Where Jupiter's cloud tops are a frigid -200 degrees Fahrenheit, VHS 1256b simmers at a blistering 800. That temperature gap is the difference between a freezer and a forge. It dictates everything that happens next. On Jupiter, the clouds are made of ammonia and water ice. On VHS 1256b, the clouds are silicate vapor condensing into grains of sand and molten glass. One world has storms of familiar, albeit exotic, ices. The other has storms of vaporized rock. The precipitation follows suit. Jupiter might rain droplets of liquid ammonia or hail of water ice. VHS 1256b precipitates a blizzard of incandescent mineral grains, a downward sandblast that vaporizes before it can land. Even the great, enduring storms are different. Jupiter's Great Red Spot is a high-pressure anticyclone, a vast, stable swirl. The storms on the exoplanet are likely far more transient and chaotic, fueled by a much more intense heat engine from within and shredded by even faster winds. This comparison does not diminish Jupiter, it redefines our perspective. Jupiter shows us the powerful, yet familiar, end of gas giant weather. VHS 1256b shows us the alien extreme, where the very chemistry of the air is rewritten by heat, creating skies that rain the stuff of continents. It is a vivid reminder that our solar system, for all its wonders, is just one page in a galactic catalogue of atmospheric possibilities. This world of silicate snow is not alone in its metallic weather. Across the galaxy, astronomers are discovering a family of planets where the skies rain metal, each with its own terrifyingly unique recipe. Perhaps the most famous is the exoplanet WASP 76b, a so-called hot Jupiter so close to its star that its day side is scorched to an unimaginable 2,400 degrees Celsius. At that heat, metals like iron do not just melt, they vaporize. The atmosphere on the permanent day side becomes a soup of gaseous iron. But the planet is tidally locked, meaning one side always faces the star in perpetual day and the other is cast in eternal night. This creates the most extreme weather engine imaginable, a temperature difference. Furious, supersonic winds, born from the pressure imbalance between the blazing day and the cooler night, sweep that iron vapor across the terminator line into the darkness. As the gas hits the shadowed hemisphere, it plummets in temperature by nearly 1,000 degrees. Just like water vapor cooling to form rain, the iron vapor condenses. It first forms droplets of liquid iron, which then fall from the sky as a literal rain of molten metal on the night side. The mechanism is starkly different from what we see on VHS 1256b. On WASP 76b, the driver is external, a relentless stellar furnace vaporizing material on one side, with planetary winds and radical cooling handling the rest. It is a horizontal weather cycle powered by stellar proximity. VHS 1256b, in contrast, generates its chaos from within. Its silicate snow is driven by internal heat and powerful vertical convection, a planet-wide churn that lifts vaporized rock from its own depths to cool and condense aloft. One world is tortured by its sun, the other boils from its own fiery heart. Yet both belong to the same astonishing category, worlds where the very concept of precipitation is rewritten in elements we associate with industry and bedrock. They tell us that the conditions for metal rain are not a fluke, but a predictable outcome of extreme physics. With every new discovery, our catalogue of bizarre weather expands, painting a galaxy far more creatively violent and strangely beautiful than we ever dreamed. The stunning visualizations of these alien storms rest on a foundation of almost impossibly delicate data. Observing a world like VHS 1256b is an exercise in cosmic detective work of the highest order because we are not looking at a picture in any traditional sense. These planets are tens of light years away, lost in the overwhelming glare of their parent stars. For most exoplanets, the primary method of discovery is the transit method, watching for the tiny, periodic dimming of a star's light as a planet passes in front of it. That tells us the planet is there and gives us its size and orbit, but little about its atmosphere. The other major method, the radial velocity technique, detects the star's subtle wobble caused by the planet's gravity, revealing its mass. Both are indirect, like sensing a person's presence by their shadow or the sway of a branch they brushed against. VHS 1256b was unusual because its immense distance from its stars allowed it to be detected directly as a separate, faint point of infrared light. But even then, it is just a dot. The James Webb Space Telescope's revolutionary achievement was to take that single, faint pixel of warmth and split it apart into a spectrum. It captured the planet's own glow, which is light that has filtered up through its entire atmosphere from the hot interior below. The telescope then spread that light out, revealing the chemical fingerprints etched within it. Think of it not as taking a photograph, but as catching the planet's breath on a cold window and analyzing the condensation. Every molecule in that atmospheric breath leaves a mark. The challenge is staggering. The signal is incredibly faint, a whisper against the roar of the cosmos, requiring hours of precise, uninterrupted observation. And the result, for all its richness, comes with a fundamental limitation. That spectrum is not a weather map. It is not showing us a specific storm cloud over a specific continent. It is an average. The light Webb collected is a blend of every part of the planet's day side that was facing the telescope during the observation. The clear signatures of silicate grains, water vapor, and methane are all smeared together from across the entire hemisphere. The patchy cloud decks we infer are a best guess from the shape and strength of those spectral lines, suggesting some areas have thicker clouds and others are clearer, but we cannot point to a longitude and latitude. We are hearing the planet's entire orchestra play at once, and from that magnificent noise, we are trying to pick out the individual instruments, their volume, and their tune. This makes the detail we have managed to extract not just impressive, but borderline miraculous. It underscores that what we know about the metallic snow is not a localized forecast, but the overwhelming character of a world, a global declaration of its stormy nature written in light we can barely see. But how do we move from a single, blended spectrum to a detailed forecast of alien weather? The answer lies not in a telescope, but in a supercomputer. To truly understand the chaotic skies of VHS 1256b, scientists must build a digital twin, a virtual planet inside a machine. They start with the raw ingredients from the James Webb data, the confirmed presence of silicate vapor, water, methane, and carbon dioxide. Then they add the fundamental laws of physics, the equations that govern how fluids move, how heat transfers, and how gases behave under immense pressure and temperature. This creates a theoretical framework, a set of rules for how the atmosphere should operate. But the real magic and the immense challenge comes in the simulation. Researchers feed this framework into some of the most powerful supercomputers on Earth. These machines divide the planet's entire gaseous envelope into a three-dimensional grid, with millions or even billions of virtual cells stacked from the deep interior to the upper cloud tops. Each cell is assigned a starting temperature, pressure, and chemical composition based on the best guesses from the data. Then the computer presses play. It calculates how heat flows from the hot core upward, how that heat drives convection, how the planet's furious rotation twists those currents into winds, and crucially, how the silicate vapor cools and condenses as it rises. The model runs this complex dance of physics forward in time, simulating months or years of planetary weather in a matter of days. The goal is to see if this virtual world, built from equations and data, naturally produces the conditions Webb observed. Does it generate patchy silicate clouds at the right altitude, or does it create a uniform global blanket? Do the predicted wind speeds match the estimates inferred from the spectrum? The models become a testing ground for hypotheses. One team might simulate what happens if the internal heat is slightly stronger, or if the atmospheric mix has more water vapor than expected. They run these variations over and over, comparing the simulated planet's final, blended spectrum to the real one from the telescope. When the digital output closely matches the real data, they know their model is on the right track, that they have likely captured the essential forces shaping that alien sky. These simulations do more than just confirm what we see, they predict what we cannot. They can show us where the most violent storms might erupt or how the cloud patterns might shift over long periods. They might reveal that under certain conditions, the silicate rain could briefly form larger, gravel-sized particles before vaporizing, or that immense hurricane-like vortices could spin off from the main circulation. The supercomputer becomes a time machine and a laboratory, allowing us to experiment on a world 40 light-years away, probing its deepest secrets from the safety of a server room. This metallic storm is more than a spectacle. It is a fossilized chapter from the very first pages of a solar system story. The silicate grains churning in the atmosphere of VHS 1256b are not just weather, they are the raw, primordial ingredients of planets. In our own solar system, the story goes like this. 4.6 billion years ago, a vast cloud of gas and dust collapsed under its own gravity. In the hot, dense center, our sun ignited. In the swirling disk of leftover material that circled it, microscopic dust grains of ice and silicate began to stick together. Over millions of years, these grains collided and combined, growing from pebbles to boulders to mountain-sized planetesimals. Eventually, through countless collisions and mergers, they formed the rocky cores of the inner planets, Mercury, Venus, Earth, and Mars. The silicates that make up our continents, our mountains, the very ground beneath our feet, all began as a fine, cold dust in that ancient protoplanetary disk. VHS 1256b shows us a stunning, alternate version of this process. Here, the silicates are not cold and inert. They are superheated, vaporized, and actively cycling through a giant planet's atmosphere. This world is so young that it exists in a state similar to the very early days of any planetary system, a time of immense heat and chaotic motion. Its atmosphere acts like a giant, continuous refinery, constantly processing these fundamental rocky materials. The profound implication is that in the infancy of a star system, processes like this could be happening on a grand scale. Imagine multiple giant planets still glowing with formation heat, each acting as a churning factory for silicate dust. Their fierce weather systems will be constantly lofting this vaporized rock high into their atmospheres, where it condenses into fine grains. Some of those grains, caught in powerful jet streams or escaping the planet's gravity entirely, could be blown outward into the cooler, calmer regions of the disk. There, far from the heat of the young star or the searing interiors of the giants, this processed silicate dust would settle. It would mix with ice and other materials, providing a steady rain of pre-processed, refined building blocks. This is a radical idea. Instead of terrestrial planets forming solely from the slow, cold accretion of primordial dust, they might also be seeded with material that has been cooked, vaporized, and condensed inside the atmospheres of giant planets. VHS 1256b offers a direct glimpse into that potential seeding mechanism. It is a window into the chaotic, dusty nursery that every solar system, including our own, must pass through. By studying its metallic snow, we are not just learning about one bizarre world, we are watching the foundational elements of rocky planets being forged and scattered, a process that may have been essential to our own existence. The metallic snow of VHS 1256b paints a sky of breathtaking violence, a place where the very elements of rock are vaporized and reformed. This immediately raises a profound and tantalizing question. Could any form of life possibly survive in such a furnace? The direct answer is a definitive no. This super Jupiter is a laboratory of extreme physics, not a cradle for biology. Its 800-degree cloud tops are hot enough to melt lead. Its atmosphere is a churning cauldron of scorching silicate grains and supersonic winds, with no solid surface and pressures that would crush any known complex molecule. The very chemical cycles we find so fascinating, the endless rain of molten glass, are processes that would utterly destroy the delicate structures essential for life as we understand it. This world is a monument to abiotic chaos, a reminder that the universe creates environments far beyond our conception of habitability. Yet, dismissing it as merely a dead world misses its profound significance. The true value of studying this hellish planet lies not in searching for life upon it, but in using it as a training ground for the search for life elsewhere. VHS 1256b is in essence a masterclass in reading alien atmospheres. Here, scientists are stress-testing their tools and techniques against the most complex, dynamic, and chemically rich exoplanet atmosphere we have ever observed in such detail. The James Webb Telescope did not just find one or two simple gases. It detected a full cocktail of molecules: water, methane, carbon dioxide, and silicates, all interacting in a turbulent, three-dimensional weather system. Learning to interpret this noisy, blended, and incredibly faint signal is like learning to understand a language by first listening to a rapid, overlapping debate rather than a single clear sentence. The skills being honed here are directly transferable to the ultimate goal, finding a world like our own. Future telescopes will set their sights on smaller, rocky planets orbiting in the so-called habitable zones of their stars, where temperatures might allow liquid water to exist on a surface. The signals from those worlds will be exponentially fainter, their atmospheric signatures whisper thin. When we finally point our most powerful instruments at an Earth twin 40 light-years away, we will be looking for subtle traces, potential biosignatures like an unusual abundance of oxygen mixed with methane, or other chemical imbalances that hint at biological activity. But how will we know if the methane we see is from microbes or from geological processes? How can we be sure the oxygen isn't being produced by a non-living photochemical reaction? The answer comes from the lessons of the silicate snow planet. By perfecting the models that explain the chaotic chemistry of VHS 1256b, scientists are building more reliable frameworks to understand atmospheric dynamics everywhere. They are learning to distinguish between the spectral signature of a global, abiotic sandstorm and the localized, persistent signal of a potential biosphere. They are refining their ability to account for how clouds, haze, and fierce winds can alter the light we see, ensuring that a future, tantalizing hint of life is not just a misinterpretation of extreme weather. This bizarre world is the ultimate control experiment, a place where we know life cannot exist, allowing us to see with perfect clarity what a complex, lifeless atmosphere truly looks like. By mastering its language of fire and metal, we are quietly, meticulously preparing ourselves to recognize the first, faint whispers of a very different story written in the light of a distant, living world. The search for more worlds of metallic snow has only just begun. The James Webb Space Telescope is poised to become a dedicated exoplanet meteorologist, with dozens of similar gas giants and smaller worlds already slated for observation in its upcoming cycles. Each new target will add another data point, another spectrum to compare. Is VHS 1256b a unique adolescent monster, or is its silicate storm a common phase for young super-Jupiters? Only by surveying many more will a true pattern emerge, transforming a single breathtaking anomaly into an understood class of planetary weather. But Webb will not be working alone for long. On the horizon, a powerful new set of eyes is preparing to join the hunt. The Nancy Grace Roman Space Telescope, scheduled to launch later this decade, carries a revolutionary instrument called a coronagraph. This is a tiny, precise mask inside the telescope designed to block the blinding glare of a star, much like using your hand to shield your eyes from the sun to see something faint nearby. Roman's coronagraph is a technological leap, engineered to directly image giant exoplanets orbiting close to their stars, worlds that are currently lost in the stellar glare. It will not match Webb's profound ability to dissect atmospheric chemistry in fine detail, but it will excel at discovery and initial characterization, finding new candidates for Webb to study in depth. It will help us answer a fundamental question: how many of these extreme worlds are actually out there? Meanwhile, back on Earth, an entirely different kind of giant is rising. In the high deserts of Chile, construction is underway on the extremely large telescope, the ELT. As its name promises, its primary mirror will be a staggering 130 feet across, collecting more light than all of today's major research telescopes combined. While Earth's atmosphere blurs and distorts light, new adaptive optics systems on the ELT will correct this twinkling in real time, with thousands of actuators bending a secondary mirror at incredible speeds. This ground-based behemoth will achieve a level of clarity once thought impossible from our planet's surface. Its power could allow it to perform a kind of rudimentary weather mapping. By observing an exoplanet like VHS 1256b as it rotates, the ELT might detect subtle changes in brightness or color across its face. One hemisphere might appear slightly darker or redder than the other, hinting at a vast storm system or a permanent cloud bank. This would be our first ever glimpse of surface, or rather atmospheric, features on a world so far away, moving us from understanding its global composition to beginning to chart its meteorology. Further into the future, concepts now on drawing boards at NASA and other space agencies aim for the ultimate goal: direct imaging and spectroscopy of Earth-like planets. Missions like the Habitable Worlds Observatory envision a space telescope so stable and equipped with such an advanced coronagraph that it could block the light of a star and directly capture the faint, pale blue dot of a terrestrial world in its habitable zone. While such a mission would focus on searching for signs of life, the technologies developed would inevitably be turned toward giants like VHS 1256b as well. We could one day see not just a spectrum of its entire dayside, but take multiple spectra of different regions, creating a crude but real map of its cloud decks, hotspots, and storm systems. We might watch in real time as a gigantic silicate storm erupts and then dissipates over weeks or months. The journey from a single pixel of light to a dynamic weather map is long, but it is a path we are now firmly on. VHS 1256b is the stunning proof of concept, the first chapter in a story that will be written by the next generation of telescopes, each one bringing a distant, fiery blizzard into sharper and more astonishing focus. The story of this distant world ignited a firestorm of fascination far beyond the halls of academia. Within hours of the James Webb findings being published, headlines blazed with a kind of poetic awe. News outlets around the globe proclaimed the discovery of the planet where it rains sand, a world with metallic snow and skies of molten glass. This was not the dry announcement of an exoplanet's atmospheric composition. It was the unveiling of a new kind of mythology written in the language of science. There is a powerful reason this particular discovery resonated so deeply. For years, the public has been told about thousands of exoplanets, catalogued by letters and numbers, their properties listed in tables of density and orbital period. These are vital data points, but they are abstract. They do not easily translate into an image in the mind. VHS 1256b changed that. The phrase silicate snow is immediately, viscerally understandable. Everyone knows what snow is. Everyone knows what sand is. To combine them into a single, impossible idea creates a cognitive spark. It transforms a distant ball of gas into a place you can almost picture, a landscape of the imagination where the weather itself is a character. This is the crucial bridge between complex astrophysics and public wonder. The meticulous work of spectroscopy and computer modeling finds its ultimate purpose when it produces an image so striking it stops a scrolling reader in their tracks. It makes the universe feel creatively alive, not just full of rocks and gas, but brimming with phenomena that defy our earthly expectations. Such moments are more than just entertainment. They are invitations. A child reading about a planet with metal snow does not just see a bizarre fact, they see a puzzle. Why does that happen? How could it be? That spark of curiosity is the seed from which future scientists, engineers, and dreamers grow. It reminds everyone that exploration is not a completed chapter in a history book, but a live, ongoing drama with new pages being written by telescopes and the minds that interpret their data. The media frenzy, then, is not just noise, it is the sound of the universe connecting. The moment a whisper from 40 light-years away becomes a story shared by all of humanity, a reminder that the cosmos still holds wonders capable of leaving us utterly breathless. This metallic blizzard is not a gentle fall of crystalline ice. The word snow here is a powerful but potentially misleading shorthand. What actually falls through the alien skies of VHS 1256b is not a delicate, six-sided flake. It is a searing mist of microscopic silicate grains, more akin to a planet-wide sandstorm turned vertical. At the altitudes where it forms, these particles might begin as droplets of molten rock, tiny spheres of liquid glass that cool and solidify into fine, abrasive sand as they descend. If you could somehow stand in that sky, you would not see a white blanket accumulating on the ground. You would witness a scorching, glittering haze, a downward rush of incandescent grit, like being inside an endlessly raging furnace where the embers themselves are made of sand. It is a precipitation of bedrock, not water ice, and it rewrites our very definition of a storm. A crucial point of clarification is that every breathtaking artist's impression you see, every visualization of these rust-colored skies and fiery downpours is exactly that, an interpretation. We do not have a photograph of VHS 1256b in the way we have photos of Mars or Jupiter from orbiting probes. What we have is a graph, a jagged, spectral line filled with dips and peaks captured by the James Webb Space Telescope over hours of painstaking observation. Each tiny trough in that line corresponds to a specific molecule, like silicate or water vapor, absorbing a very specific color of infrared light. The artists and scientists work together to translate that chemical barcode, that single line of data, into a scene our human brains can comprehend. They take the confirmed ingredients, silicates, water, methane, and the known physics of heat, pressure, and condensation, and build a plausible visual model. The result is a masterpiece of informed speculation, a bridge between raw numbers and human imagination, but it is not a snapshot. It is the closest we can come to seeing a world whose light is too faint for any camera to capture directly. Perhaps the most profound takeaway from this entire discovery is not how alien it is, but how familiar the underlying rules are. The processes forging this metallic snow are not magic, nor do they require new, undiscovered physics. They operate on the exact same principles we observe in our own kitchen or our own skies, just pushed to a staggering extreme. Condensation is condensation, whether the vapor cooling is water or vaporized rock. Convection is convection, whether the rising plume is warm air or a column of superheated mineral gas. The phase changes between solid, liquid, and gas follow the same thermodynamic laws, even if the substance undergoing the change is in statite instead of H2O. This world is a natural laboratory demonstrating that the universe is consistent. The same chemistry and physics we've painstakingly unraveled here on Earth through experiments and observation apply with perfect fidelity 40 light-years away. The staggering difference is not in the rules but in the environment. By applying our known laws to these alien conditions, immense heat, crushing pressure, and exotic ingredients, we can predict and now confirm the existence of something as wonderfully bizarre as a sandstorm that falls from the sky. It means that for all its terrifying beauty, VHS 1256b is ultimately knowable. Its chaos is not random. It is a complex, solvable equation written in fire and metal, a testament to the universal language of nature spoken from one end of the galaxy to the other. That single, jagged line of data is a key that unlocks a universe of possibilities. For centuries, our understanding of weather, of planets, and of nature itself was confined to the examples in our own solar system. We knew of water cycles and ammonia clouds, of frigid ice giants and rocky deserts. Our imagination, though vast, was subtly tethered to the familiar. The discovery of a world where the sky rains sand shatters that tether completely. It tells us with the quiet authority of hard evidence that the cosmos is far more creatively violent and strangely beautiful than we ever dared to assume. This is not just about adding one bizarre planet to a catalogue. It is about a fundamental shift in perspective. VHS 1256b is a single data point, a pixel of light from 40 years in the past, yet it forces us to rewrite the entire chapter on planetary atmospheres. If conditions can align to create a global blizzard of molten silicate on one world, what other recipes exist? What might be brewing under the opaque, methane-rich skies of a colder giant, or in the super-rotating winds of a tidally locked lava world? The existence of this metallic snow proves that the palette of planetary physics is not limited to the colors we see at home. It suggests an almost infinite diversity of weather, of chemistry, of entire global systems operating on logic we are only beginning to comprehend. This discovery challenges a deeply ingrained, Earth-centric view of nature. We have a tendency to see our world as the standard, the normal template against which everything else is measured. But the universe has no such bias. It will happily combine heat, pressure, spin, and chemistry in endless permutations, following its consistent laws to produce outcomes that seem like pure fantasy to us. A planet where it rains rock is not an error or an oddity. It is a direct and inevitable consequence of those universal laws playing out in an environment utterly unlike our own. It is a reminder that we are not the center of a cosmic story, but rather avid readers of a book with more chapters than we can count. Each new telescope, each new spectrum adds another sentence, another paragraph of that story. And if this is what we find when we look at just one young, turbulent giant, it hints at a galactic library filled with tales of storms we cannot yet name, precipitations we cannot yet conceive, and worlds that will continue to expand the very boundaries of what we believe is possible. The awe we feel is not just for the spectacle of the metallic snow itself, but for the vast, uncharted territory it represents, waiting silently in the dark for our instruments and our imaginations to catch up. To truly grasp the violence of this world, let us conduct a brief and purely theoretical thought experiment. Suppose a spacecraft of impossible durability could somehow survive the journey and hover just above the cloud tops of VHS 1256b. The first thing to strike you would not be sight but sound, or rather the overwhelming sensation of vibration. the hull would scream, not with the whistle of wind, but with a deep, resonant roar as supersonic rivers of gas, thousands of miles per hour fast, shear across its surface. It would feel less like flying and more like being anchored in the heart of a perpetual rocket engine blast. Peering out, your eyes would struggle to find a horizon. The sky itself is a dense, churning ochre haze streaked with darker bands of condensing mineral vapor. Light comes from two sources, both alien. Above, the twin parent stars are not blazing disks but piercingly bright points, casting faint, double shadows that shift and blur in the turbulent air. The more dominant glow, however, rises from below. The planet's own internal furnace shines upward through the thinner patches of cloud, bathing everything in a hellish, ambient radiance like standing over an open forge. Then comes the precipitation. It would not fall in gentle flakes, but as a constant, searing mist. Microscopic particles of silicate, some still molten, would pelt the viewport and hull with a sound like endless, abrasive sandblasting. Each impact, multiplied by trillions, would create a shimmering curtain of incandescent grit, a blizzard of embers that never settles, only vaporizes and rises to fall again. The heat, even at this cloud-top altitude, would be an oppressive 800-degree wall. There is no air to breathe, only a thin, scorching soup of hydrogen, helium, and mineral vapor. This is not a place for life or even for machinery for more than a fleeting instant. It is a realm of pure, elemental fury, where the very processes that build continents on comma worlds are unleashed as a permanent global storm. The most astonishing discoveries often begin not with a telescope but with a human eye. While the James Webb Space Telescope collects the raw data, the monumental task of interpreting it relies on a global network of minds, and that network now includes you. This is the frontier of citizen science, a collaborative movement where professional astronomers partner with the public to sift through the universe's information. Platforms like Zooniverse have transformed your curiosity into a genuine scientific tool. On these websites, volunteers from around the world log in to help classify galaxies, spot new craters on Mars, or identify unusual light curves from distant stars. The principle is beautifully simple. Computers are excellent at gathering and storing immense datasets, but the human brain remains uniquely gifted at pattern recognition, at spotting the odd detail that an algorithm might overlook. For exoplanet science, this means volunteers might scan through thousands of graphs of starlight, looking for the telltale, repeating dip that signals a planet's transit. They might help tag interesting features in simulated atmospheric data, training the very machine learning models that will one day analyze planets like VHS 1256b. The data from Webb is exquisitely complex, a symphony of spectral lines that takes years for a small team of experts to fully decode. But by distributing small, manageable pieces of that data to a crowd of passionate observers, the process accelerates. A volunteer might spend just a few minutes on a coffee break reviewing a handful of images or graphs, but collectively, those minutes add up to thousands of hours of analysis that would be impossible for any single research institution. This is not busy work, it is foundational research. Volunteers on Zooniverse have co-authored scientific papers, having directly contributed to the discovery of new types of celestial objects. Their participation does more than just advance the science, it redefines who gets to be a scientist. You do not need a PhD in astrophysics to contribute to our understanding of metallic snow or alien weather. You need only an internet connection, a little guidance, and that innate human drive to explore and categorize the world around us. This empowerment is perhaps the most profound legacy of discoveries like the silicate storm planet. It demystifies the process, breaking down the wall between the public and the professionals. It turns the awe you feel when you see an artist's impression of a world with sandstorms in its sky into a tangible action. That curiosity is the most valuable instrument we have. By joining a project, you become part of the distributed neural network scanning the cosmos, a participant in the ongoing story. The next big discovery in exoplanet science might not come from a lone astronomer in an observatory, but from a teacher in Lisbon, a student in Tokyo, or a retiree in Chicago, who noticed a tiny, anomalous blip on a screen and decided to flag it for a closer look. This entire spectacle of metallic snow boils down to a specific, extreme recipe. For a world to host such a phenomenon, it requires a precise and violent alignment of cosmic ingredients. First, you need the right kind of planet, a massive gas giant with a searing internal furnace. This is the engine, the primary heat source that keeps the entire system in motion. Second, its atmosphere must be rich in the raw materials, specifically silicate minerals like those that form sand and rock. Third, you need a powerful delivery system, which comes in the form of relentless convection currents, the planet-wide updrafts that carry that vaporized rock from the infernal depths up into the cooler skies. Fourth, there must be a region high in the atmosphere where temperatures drop enough for a phase change to occur, a condensation zone where the vapor can cool and coalesce into particles. And finally, you need the cycle itself, the endless loop where those newly formed grains fall, are reheated and return to vapor, only to rise and begin the process anew. VHS1256b is not just a world that happens to have one or two of these conditions. It is a perfect, raging storm of all five. Its immense mass and youth provide the intense internal heat. Its composition, likely inherited from its primordial birth cloud, supplies the silicate vapors deep within. Its furious spin and heat-driven dynamics generate the supersonic convection. Its vast atmospheric structure creates the necessary temperature gradient for condensation high above, and its entire gaseous envelope is locked in that perpetual, scorching dance of creation and destruction. Remove any one piece of this recipe and the metallic snow would cease to fall. It is a fragile, ferocious balance, a demonstration of how ordinary physics, when pushed to its limits under alien conditions, can produce a sky that rains the stuff of stone. From a faint infrared smudge in a Chilean telescope to a chemical portrait of a world in chaos, the journey to understand this planet of metallic snow is a story written in human ingenuity. It began with a patient survey of the southern sky, a simple detection by the Vista telescope that marked a point of interest, a faint glow 40 light-years away. That single point of data was a question hanging in the dark. The answer required an instrument of unprecedented power, the James Webb Space Telescope, with its golden mirrors and exquisite spectrographs capable of tasting light. It transformed a pixel into a spectrum, a jagged line into a saga of vaporized rock and supersonic winds. This was not a single eureka, moment, but a chain of them, each link forged by curiosity and engineering. The wonder we feel is not just for the alien storm itself, but for the fact that we can know it exists at all. We have reached across the void with mathematics and machinery and listened to the whisper of a world's atmosphere, deciphering a weather report from a furnace. That achievement belongs to everyone who ever looked up and wondered, to the engineers who built the tools, and to the scientists who learned to read the universe's hidden language. So the next time you find yourself under a clear night sky, take a moment, look toward the constellation Corvus, the Crow, and know that in that direction, a young giant endlessly cycles rock through its scorching heavens. Let that reality sink in. Our catalog of cosmic weather has just begun, with even more powerful telescopes on the horizon, from the ground-based extremely large telescope to future space observatories. We stand on the threshold of discoveries that will make metallic snow seem almost ordinary. The universe is patiently waiting, holding secrets of storms and skies we cannot yet dream of, ready for the next curious generation to point a new eye toward the stars and ask what else is falling from the alien sky. The constellation Corvus holds a secret, a world that redefines the very meaning of a storm. We have traveled through its scorching skies together, from the first detection to the detailed chemistry of its metallic snow, and witnessed how a single point of light can unfold into an epic of alien weather. This journey reminds us that the universe is not just vast, it is endlessly inventive, crafting realities from the same physics we know, but in combinations that stretch our imagination to its limits. Now we want to hear from you. After exploring this world of silicate blizzards, which exoplanet weather phenomenon do you find the most bizarre? Is it the iron rain of WASP-76b, the possible gemstone showers of HATP-7b, or something else entirely? Let us know in the comments below and tell us what is the next great mystery you hope the James Webb Space Telescope will unveil. If you enjoyed this deep dive into a planet where the sky rains sand, please give this video a like. It helps us continue exploring the cosmos together. For more journeys to the edges of our understanding, be sure to subscribe. As we look up at the night sky, we carry with us the words of the astronomer Carl Sagan, who said, "Somewhere, something incredible is waiting to be known." Until our next adventure among the stars, keep looking up.